In this talk, we'll finally see this equivalence that we've been talking about for so long. So we now know what the functors gamma and lambda are. We now know what these guys are. We know what the category of Etale spaces is. And now we can finally start talking about this equivalence that I've claimed exists. We know what Etale spaces are, so we can start talking about this equivalence. So the first order of business is to check that gamma and lambda, as drawn in this diagram, actually make sense. So I've claimed this repeatedly. I've claimed repeatedly that if you start with an Etale space, apply gamma, you'll get a sheaf. If you start with a sheaf, apply lambda, you'll get an Etale space. But I've never said anything about why it's true. And I'm going to persist in not saying anything about why it's true. But I do want to sort of tell you what the more general fact is, which is maybe revealing as to how you would check this. You kind of can see what's essential. So let me give these two facts, and then we'll start talking about the equivalence. These two facts are just to establish that the diagram makes sense as I've drawn it. So fact the first, this is that, well, let's let F be any pre-sheaf. Be any pre-sheaf on X. So not necessarily a sheaf, just some pre-sheaf. Then, this is the first fact, then lambda of F is an Etale space. Over X. So, in other words, if you start with any pre-sheaf over here and apply lambda, you don't just get some space, you actually end up in this subcategory. So anytime you start with a pre-sheaf and apply lambda, you will actually land in the category of Etale spaces. Maybe I'll indicate this to make the diagram even more crowded by drawing this line. So this is where lambda really lands. And the similar fact is true for gamma. So this is fact the second. So let's let this P, or E via P, be any space over X. So not necessarily an Etale space, just some random space over X. Then you can guess gamma of E is a sheaf. Is a sheaf on X. So in other words, when you start with some space and apply gamma, you don't necessarily land up in, or you don't land just in pre-sheaf land up here, you actually end up in the subcategory of sheaves. So maybe I'll draw this, and this is gamma. So in particular, the bottom part of this diagram makes sense, right? In particular, things which I said down here are reasonable. It is true that if you start with an Etale space and apply gamma, you'll get a sheaf. More is true, right? If you start with any space and apply gamma, you'll get a sheaf. But in any case, these two things are true, so this makes sense. You do, in fact, stay in this kind of circle when you apply gamma and lambda. Now let me just make a side remark about this. So notice there's some sort of refinement going on. All right, there's some refinement going on through each of these facts, and that things end up being better than you might initially hope them to be. So maybe initially you start with some pre-sheaf, you apply lambda, you think, I'm just going to get some arbitrary space. There might not be anything nice about it, but it turns out that space is quite nice. It's in fact an Etale space. And similarly, this fact says you get something nicer than what you might expect. If you start with any space and apply gamma, you might think you would just end up with a pre-sheaf, but you actually end up with a sheaf, something with more structure. So there's this kind of refinement process going on when you apply gamma and when you apply lambda. And that'll be important to us later because, well, you can compose these things going back in the other direction, right? If you start with some pre-sheaf F, maybe I'll say pre-sheaf, and then anticipating what will happen later, let me just say we'll do a space over X. And this will be a sheaf, and this will be an Etale space. I'm just filling this out now, so I don't have to change colors again. So if you start with some pre-sheaf f and you map it over into gamma of lambda of f, well, we apply lambda of f, we get an Etale space, and then we apply gamma and we get a sheaf. So we've gone from a pre-sheaf f to this actual sheaf gamma of lambda of f. And we'll see later this is secretly sheafification. This is secretly the sheafification functor. And there's refinement on the other side of things too, right? If you start with some random space e over x, and you do this thing, you'll end up not with the original space again, but you'll end up with an Etale space, which I guess we'll call lambda of gamma of e over x. So there's this refinement process when you apply these two things. Alright, so I'm not going to prove these two facts, at least not in the mainline videos, but these two things are true. And because they're true, the diagram makes sense. The diagram that I drew above. This diagram. Okay, so now let's talk about why gamma and lambda are going to form an equivalence of categories. So, well, what do we want? So we want to show, we want that gamma and lambda form an equivalence of categories. Well, what does that mean? That means two things. It means we kind of have a homotopy equivalence going on here. We'll have that gamma lambda, that functor, is isomorphic to the identity functor. And we'll also have that the identity functor is isomorphic to lambda of gamma. Maybe I should point out that these are not the same identity functor, right? So if we apply lambda, we start with a sheaf, we apply, or start with pre-sheaf, we apply lambda and apply gamma. So this is the identity on the category of sheaves. And this is the identity on the category of Etale spaces. But this is just what an equivalence of categories is in our case, is all that I'm saying. I've just written down the condition for an equivalence of categories. This is what it means for gamma and lambda to form an equivalence of categories in this case. So what I'm going to do is describe what the maps are. Well, maybe I should say what I'll do. So what I'm going to do is describe maps. I'll describe a map from the identity to gamma of lambda, and I'll describe a map from the identity, the other identity, to lambda of gamma. So I'm going to say what these things are, but I'm not going to prove that they're isomorphisms. At least not in the mainline videos. So I'll describe the functor morphisms, but I'm not going to check that they're isomorphisms. And we also mentioned that when we start talking about this, just as a forewarning, there are going to be a lot of naturality conditions that I ignore. So I'm basically, let's start with this one for example. Basically I'm going to say, given a sheaf f, let's describe a map going from f into gamma of lambda of f. This is what we're about to do in a moment. And really I should check that this is natural, right? I should check that these maps that I'm going to define, they actually stitch together in order to form a functor morphism in the right sense. You know, there's some sort of naturality which should be going on. But I'm not going to check that. So this won't be a kind of foolproof. This will not be a full proof. In general, it seems that no one checks naturality, and I'm not going to either. It's just not because it's particularly difficult, just because it's kind of a pain, and there are a lot of little things to check. So people don't do it in practice. Well, maybe some people do it. Graduate students who are forced to do this kind of thing check it, but I think that in the real world, people don't. And by the real world, I mean pure Platonic abstract mathematics, of course. Okay, so let's define these maps. So, first goal. Given a sheaf F, define a map F into gamma of lambda of F. And then, of course, our second goal will be to do the other thing, which would be given a space, I guess I should say an Etale space, over X, define a map from E into lambda of gamma of E. So I want to define these two maps. They will be isomorphisms, these things that I'm about to define, this guy and this guy. They will be isomorphisms, but I'm not going to prove that. So let's start with this one first. We want to define a map from F into gamma of lambda of F. Okay, so how do we specify a pre-sheaf map? We have to specify it on every open set. So let's let U be inside of X. So we want to describe some map from F of U into gamma of lambda of F evaluated at U. Now again, I'll define this for all U. Really, that's not quite enough. There should be some sort of naturality that I check, right? I need to check that it commutes with the restriction maps. But I'm not going to do that. I'm just going to define it on the sets. I'm going to define it on the open sets. So what is this map? Well, to define this map, let's kind of unravel what this guy is over here. Let's kind of unravel what this thing is. So, well, this is gamma of lambda of F evaluated at U. So what does gamma do? Gamma is this sections functor, right? So this is equal to sections. This is equal to sections from U into lambda of F. And kind of remembering how we define lambda of F, this is sections from U into this disjoint union over all points X and X of the stocks F of X. Kind of forgetting about the topology for a second, let me just write down what the set looks like. So we have to figure out how to define some map from F of U into this set. And it is not hard to guess what this map is going to be, because we've already defined some element in here associated to things inside of F of U. So what this map is going to be is the map that sends S in here to S dot. And S dot is this thing that we defined earlier. What S dot is, just to briefly recall, maybe I'll put a backlink in here for a longer recollection, but what S dot is this map going to, I guess it should be all of the U inside of U of F of U, and what it does is send the point U to the collection of S, or the image of S in the stock at U. That's what this map is. So shorthand is this over here, S maps to S dot. And all I've done over here is remind you what S dot is, but I'll probably put a backlink in anyway. Okay, so we've defined what this map is, and I claim that it's going to be an isomorphism. And again, I'm not going to prove this, but maybe I'll just say what are the things you could worry about, and how do the conditions sort of guarantee that this will be an isomorphism. So one thing you could worry about is injectivity, right? If this is an isomorphism, we basically just have to check that it's a bijection. So, I mean, again, I'm ignoring a lot of naturality in saying that, right? I'm ignoring some sort of structure, but let's just let's leave that at bay for the moment and just say that we have to check that this is a bijection, right? In order to check it's an isomorphism, maybe I'm going into more detail about this than I should, but now that I've started, let me finish. I want to check that S maps to S dot is an isomorphism. So you might ask yourself the question, is it injective? Well, that question basically is if S dot is equal to T dot, or S and T are inside of F of U, does that imply that S is equal to T? Yes, it does. This is the separation property of sheaves. So this is a property that separated pre-sheaves will have. Okay? This is, in other words, maybe if you haven't heard that terminology, I'm not sure if I used it in earlier videos. In other words, there's the sheaf property, which says that if you've got maps, if you've got some open set and you've got some open covering of it, and you have elements in F of U and F of the original thing which agree on all restrictions, then those elements are equal. That's the separation property of sheaves. That separation property is what guarantees injectivity. Okay. So surjective, that's the other part of being a bijection, right? So in other words, is it true that if you've, I guess the way of saying that is every element, oh, I don't know, let's call it every element F inside of lambda, this is just rephrasing surjectivity, inside of gamma of lambda of F of U of the form F is equal to S dot for some S inside of F of U. This is just rephrasing the surjectivity condition. I'm just sort of going through the definition and seeing what it means in practice in this case. So is this true? This condition is equivalent to surjectivity. We want to know if it's true. Yes, this is also true. And this has to do with the gluing property of sheaves. It's the gluing property of sheaves that will make this work. So that's why we kind of need to start with a sheaf in order to make this equivalence go through. In other words, in order to get this isomorphism. But that's why it works. Okay? So I think that's pretty much everything that I want to say about this map. That's everything I want to say about this. I've described what it is. I've said a little bit about why it's an isomorphism. Of course, I haven't actually proved anything, but that's sort of how the proof goes. So let's talk about this guy now. So let's talk about this map. Sorry, let me go back. We want to talk about this map now. So, all right. Well, we want to define a morphism from E into lambda of gamma of E. And again, as we did with the sheaf case, let's just kind of cash out what this guy is. Let's sort of figure out what this thing actually is. So this is, of course, lambda of gamma of E. So that's equal to this disjoint union. As a set, this is equal to a disjoint union of all x inside of x of gamma of E of x. So this thing and this thing are the same. I'm just sort of writing down the definition of lambda. And we know, this is a lemma that I mentioned earlier, and we know that this is, instead of all x inside of x, we know what this stock looks like. This is P inverse of x. Here P is the structure morphism. P is the structure morphism from E into x. So these stocks of this functor, of this pre-sheaf gamma of E, those are just the fibers of P. So given that that's true, what we're really trying to do is define a map from E into this set. And it is not very hard to guess what this is either. So set-wise, E is equal to this set, right? Because we've taken all of the fibers, we've looked at all of the inverse images, this gives us back all of the points of E. So set-wise, E is just equal to this disjoint union. So we can just define the identity map. Just takes the point E to the point E. So you start with some point E inside of here, you figure out which fiber it's in, and then you send E to that point in that fiber. Okay, so that defines it on the level of sets, but you could worry about whether this map is continuous, right? Maybe even though these sets E and this weird thing, they're the same as sets, maybe they're topologically different, right? So we've defined this identity map, but maybe it's not continuous. Well, it is, and it is in fact a homeomorphism. So that's all I'm going to say about that. Okay, so let me get rid of some of this cordoning off. Let me get rid of some of the superfluous stuff so that we can focus. So we've defined these two maps now. We define this map, and we define this map. And I've claimed that both of them are isomorphisms. And if you believe me that both of them are isomorphisms, and if you believe me that they are defined naturally, right? I haven't said anything about the naturality conditions, but if you believe the naturality conditions are satisfied, then we're done. Because we have indeed described these maps. We have indeed described these maps. And if you believe that things are isomorphisms, and if you believe the naturality conditions, these are actually functor isomorphisms. Functor isomorphisms between gamma lambda and the identity, and between the identity and lambda gamma. So that shows the equivalence. And that's it.